Okay, so hello everyone. Good evening. Can you hear me?
Yes, we can.
Yes, sir.
Okay, thank you. Just waiting 1 minute, then we'll start.
Hello, sir.
Yes, please.
Hello. Yeah, so you said like you will give us like some homework also, but I didn't find any
Okay, I will
homework in the
submit it. I
list.
will submit that. You can easily get it all of you. Okay, so I will submit and I will inform. No problem.
Okay, thank you,
As well
thank
as
you.
also all of recorded class, I will submit. Then you can easily get it. Okay, so we will start today's session. So basically, today is our fourth number of day, and today's session mainly we try to focus on LST or urban heat island or UTFVI index, these type of things we try to focus. Okay, so let me share my screen. And after completing the 3 hours live training, then we talk about the problem solving class for the previous class or other problem. We try to discuss about that. Okay, so let me share my screen. Okay, can you see my screen? Is it visible? Can you see my screen?
Yes, we can.
Okay, thank you. Okay. So basically today's session I try to discuss about that how to remove cloud and haze from satellite imagery, as well as we also discuss about that how we can easily visualize the DEM data, mainly using the DEM data, how we can easily work for the hill shade map, slope map, and aspect map using Google Earth Engine. As well as we also discuss about that LST monitoring, mainly Landsat satellite imagery. So previous class I already discussed for MODIS, okay, how we can easily use the MODIS satellite imagery and make the time series chart, as well as also make the LST map using MODIS satellite imagery. But MODIS is not the good resolution imagery. So for that, when you want to get the more accurate result or you want to make the more better map, then we can use the Landsat satellite imagery, because Landsat is only for the 30-meter pixel size. So that's why when you are use the Landsat imagery, then you also get the more better map for land surface temperature. And after the land surface temperature, we also discuss about the urban heat island, because LST and urban heat island is related topic. So that's why I also try to explain about that how we can easily find out that urban heat island region for any specific cities. I will try to show the example, then you can easily get it. This is the urban heat island. Where is the high, where is the low? We can easily get it. As well as we also discuss about that urban thermal field variance index, mainly UTFVI. As well as we also discuss about that how we can easily make the time series chart of LST or urban heat island or UTFVI index. How we can easily make the time series chart. We will also try to discuss about that, as well as how to calculate for average, maximum, minimum, or NDVI for any specific region. We also discuss about that for a statistical purpose. You also need this type of value. So let's go ahead and discuss about the one by one, all of topic, and then for the practical example, then you can easily get it how it will work. So let's go. So first of all, here you can see this is the one kind of LST map using Landsat satellite imagery, and this is the study area of Dhaka city boundary. Okay, so from this map we can easily get the idea where is the high temperature, where is the low temperature. We can easily get the idea. Okay, so I also described all of those things, how we can easily create this type of map, as well as we can also create the urban heat island map. Okay, then urban thermal variable field strength index UTFVI. Okay, as well as, so let's go try to one by one to complete. So if you want to simply search on your any scientific journal, then we find out the lot of method for using the Landsat imagery. So just simply go to the Google Scholar, then you can easily find out the lot of topic related to the LST or urban Thailand. Also other topic you can easily get it from here. Okay, so this is the one paper for the assessing the predicting land use, land cover, and land surface temperature and urban thermal variable index using Landsat for Dhaka metropolitan area. Also, you can see the modeling the impact of the land use, land cover, and urban thermal characteristics in Kuwait. Okay, this is the two paper. You can also follow, get the idea how it will be work. Or if you want, you can simply search the randomly. Suppose I simply search here randomly LST using Landsat. Simply search. Then related to this topic, I get a lot of paper. Okay. Suppose here you can see the different types of paper. Algorithm for automated mapping of land surface temperature using Landsat 8 satellite data. Or a study of the predicting land surface temperature using Landsat data. Comparison of our algorithm. So different. Suppose I just simply click on the first one, and then I want to check it. So basically, this is one kind of paper, algorithm for automated mapping of land surface temperature using Landsat 8 satellite data they are using here. And if you want to check their method, so basically you can get the abstract. You can easily find out all of summary of this paper. So I want to focus on the method. Okay, so introduction, data, and method. So in this case here you can see basically they are used here the Landsat. They are used the AirDAS Imagine. Okay, so AirDAS Imagine is one kind of geospatial software for remote sensing analysis. AirDAS Imagine. But in this time we are not using the AirDAS Imagine. We try to develop this model using Google Earth Engine, write the code, and then develop this type of model. So in this case, they are use the Landsat 8 satellite images. Okay, and there find out the TIR band, mainly band 10 or brightness temperature band. Okay, basically this band 10 Landsat 8 is available for the band 10, and this band 10 is estimate the brightness temperature. Okay, brightness temperature, as well as band 4 and band 5 used for calculating the NDVI. So from here we can get the one decision, basically two decision. We need to create the estimate the brightness temperature using the band 10 of Landsat 8 satellite imagery, as well as we also need to use the band 4 and band 5 to calculating the NDVI. Okay, so these two things we also need. Further, here you check the other topic. So here you can see basically they also put this type of algorithm. First of all, they input the band 10, band 4, and band 5. Basically, band 10, they are calculated the mainly brightness temperature. And from the band 4 and band 5, they are calculated the NDVI. Okay. And then calculating the proportion vegetation. Okay. Basically, after calculating the NDVI, from the NDVI, they also calculate the proportion vegetation or fractional vegetation. Okay. And from here, they are calculated the emissivity, mainly surface emissivity. They are also calculated. And finally calculated the both of brightness temperature and emissivity, both of things they are used, and then calculate the LST and show the LST result. Okay, so this is the one kind of algorithm. So basically all of algorithm have the same process. So here you can see the conversion of radiance at sensor temperature. So this is the formula about that. Okay, so you can see the formula is that K2 divided by logarithm of K1 by L plus 1. Then this is the value, just simply subtract, then we can get the degree Celsius result. Okay, so this is the one kind of algorithm. Okay, so you can see also the calculating the NDVI. Okay, for calculating the NDVI, also you can see the calculating the proportion of vegetation, mainly fractional vegetation or proportion of vegetation. This is the equation: NDVI minus NDVI minimum value divided by NDVI maximum value minus NDVI minimum value, then power 2. So this is the formula for calculating the proportion vegetation or fractional vegetation. Okay, and then you also calculate about the surface emissivity. Okay, so here you can see they are calculating the land surface emissivity using this type of formula. And further they are use calculate the LST using this formula. Okay, so this formula basically BT, mainly brightness temperature, their brightness temperature divided by 1 plus lambda brightness temperature divided by rho, then multiply with logarithm, mainly emissivity, surface emissivity. This is the emissivity. Okay, so this is the one kind of algorithm to estimate the LST. Also you can see we can also use the validation, mainly check the accuracy. So for that we need the ground truth data. Further we can simply use it to for the validation. Okay, so also you can see there in this case they are using the Iridus Imagine software and calculate this type of things and also publish the paper look like that. So you can see there's a lot of paper is already published for the different purpose. Use the LST and they are do for this type of thing. So here you can see this is another one. Monitoring land surface temperature in bar.city, its surrounding using Landsat imagery. Just simply open it. So you try to check some paper. Okay, then try to develop. So if you want to find out the literature gap and further if you want you can also make the more better map for your publication. It also possible. So here you can see this is the paper. Basically this paper you can see the objective to analyze the special temporal LST, and also they are compared with the land use land cover comparison. Okay, so in this time they are use the two things, LST and its variation with land use land cover composition, and they are also make this this type of paper. So in this time we talk about the method. Just I simply open the method section. So here you can see this is the study area, and their data basically they are used at the Landsat satellite imagery, and also write about the acquisition time for your satellite imagery and the source. Okay, they are also using they take the image for USGS Earth Explorer website, and they are also used at the Google Earth Engine also to validate the ground classified. Again, you can see the method. So basically in this method, so first of all they are image preprocessing. In this case they are use the long term analysis or LST. For LST 1987, then LST 2002, 2017. Okay, they are using here. So that's why they are need to use the Landsat 578, because for Landsat 5 you can see for Landsat 5 they are using the 1987, Landsat 7 2002, and Landsat 8 they are using the 2017 satellite image are used. Okay, and they are also apply the image classification using the support vector machine. So basically, when I talk about the land use land cover classification using the different types of algorithm, then you can easily do it. This type of classification for land use land cover using the different types of algorithm. So in this time we focus only LST. Okay, so you can see the LST algorithm. Mainly they are use this type of you can see. In this case, they are also use the same equation. They are calculate the NDVI. Okay, so NDVI use this, and further also you can see from this NDVI they calculate the proportion of vegetation, mainly fractional vegetation. They are also calculate about that. And if you want to check, they are also calculate this type of brightness temperature. Okay, and finally they calculate about the LST. Okay, LST. So this is the another paper. In this paper, they also combine the LST and land use land cover at the same time, and then also make this type of paper. Okay, so you can also get a lot of paper regarding this topic. Okay, if you want, you can see suppose this is another paper. So basically, in this paper here, you can see they are also you also use here the urban heat island. Okay, so basically USI. So basically, they use here this type of formula for indicating about the urban heat island. So TS minus TM divided by TSTD. TS mainly LST. LST subtract with average LST divided by standard deviation of LST. Then we can easily get the urban heat island, normalized urban heat island. Okay, we can easily do it. So this type of things practically how we can easily do using Google Earth Engine. So today's session I will try to explain, and further we also create the map. Okay, so let's go. Just I simply open my code editor. So you can find out the lot of paper is available. Just simply search on the Google Scholar or ResearchGate. Then you can easily get it. Any kinds of paper. Okay, sir, related to the crop or agriculture. There are a lot of things is available already. So simply search in here. Suppose cropland, LST and cropland using Landsat. So just simply LST and cropland using Landsat. So then we can easily get, according to this keyword, we can easily get lot of paper. Suppose here you can see the impact of a special temporal land surface temperature on the cropping pattern and land use land cover changes using the satellite imagery for this district Punjab. Okay, so you can read this paper, then you can easily get the lot of idea how it will be work and what is the method they are using here. Also you can see the different paper. You can get that the irrigation project land surface temperature up from Landsat 8, the area and for irrigation project. Okay, also you can see the estimate the land surface temperature to study urban heat island effect. So there are a lot of things we can easily get. Just simply search, okay, and then you can easily get this type of paper. And from this paper, mainly you try to read the abstract, then also read about the data and method, and then this type of method you try to develop using Google Earth Engine. So this is the best practice. When you become a developer, then you try to read the method first, and this type of method try to develop. If you want, you can also develop this type of method for your own study area. Further, if you want, you can also write the scientific paper and you can also publish. Okay, a very high impactful journal. Okay, so this is the one way. Simply search any kinds of topic, any kinds of keyword in the Google Scholar. We can easily get a lot of paper. As well as if you want, you can simply go to the ResearchGate. So this is another source, or we can easily get the different types of paper, different types of things. We can easily get it from here. So from here you can easily get the different types of paper. Simply search your paper or anything, any related paper. Then you can easily get the lot of paper from here. And further, we can easily read the algorithm, or you can also use it for our research work. So suppose I simply search here the paper, simply search suppose LST and LULC. Okay, simply I use it and then run search it. So now this LST and land use land cover combination already published lot of paper. So now we can easily get all of paper from here. You can see the special temporal analysis, international airport development impact of the LULC and LST. Okay. Also you can see about that the assessing the land use changes with LST through NDVI and NDVI. Okay, and special indicators. So we can easily get a lot of paper from here. Just simply search and further read the algorithm or study or method, then try to develop this type of things using Google Earth Engine. Or if you want, you can also write the very good paper from here. So this is the way. So we can also use here the Google Scholar, or if you want, you can also use here the mainly you can also use here that the ResearchGate. Okay, then we can easily find out the lot of paper. Okay, so related to your field. Okay, then simply search and read the method and algorithm. Further, this type of algorithm or method, just try to implement using Google Earth Engine, and then try to make the paper, scientific paper, and then publish. Okay, so basically after completing the total 7 days online training program, anyone have any interest to the collaboration for scientific paper publication, then you can easily contact with me, because we are also providing this type of work for the collaboration. Suppose we are just make the collaborate, and then further we try to make the publish the paper for scientific journal. Okay, some part you can do, some part I also do for analysis, or other part and you also do for the other part. Then we are just make the collaborate for our publishing research paper. So these things is also possible after completing the total 7 days online training program. If you do this type of work for collaboration, then you can easily connecting, okay, and also work for the different types of scientific paper publication or scientific journal publication. We also work for that, no problem. Okay, so now move to the class. Okay, so in this case, we already show different types of algorithm for the different types of paper for LST. Okay, so now I will show you that how we can easily use this type of algorithm we can implement in Google Earth Engine. So our main target is that LST. Okay, so just I simply open my satellite imagery. So in this case for LST, we are using here the Landsat satellite imagery. Just I click on here, and then you find out your Landsat. Suppose I want to use the Landsat 8 satellite imagery. And for the Landsat 8 satellite imager, we can get this type of top of atmosphere and surface reflectance. So basically, when you want to find out the LST mapping, mainly land surface temperature, then we have to use the surface reflectance imagery. Okay, because surface reflectance imagery have a band. This band called the brightness temperature. So you can see the brightness temperature band, because for the estimating the surface temperature, we need the surface temperature, mainly STB10. So this is the band. It's called the band 10 surface temperature. So we can easily use this band, and further we can easily estimate the LST for our study area. Okay. So now, first of all, this image we need to import in our code editor. Just simply copy. And further paste here. Okay. And okay, I also increase my screen, and you can get more better view. Okay. And then I give a variable name. Suppose my variable name is that L8, then equal. So just I simply import my image collection, as well as I also need to import my study area, mainly which area I want to observe for LST or Arvanite Island or others. So for that, suppose in this case, I want to choose my study area for a specific country, or if you want, you can also do for a specific boundary. It's also possible. So you can easily do it for it simply from the asset tab. Simply import your own study area. Okay. Suppose in this case, I want to do for this work for a specific country. Suppose I want to do it for Kuwait. Okay, suppose this is my study area. For the whole Kuwait, I want to identify for LST mapping. Or China. Okay, okay, if you want, you can also do it, no problem. Okay, so I will try to make the China. Okay, suppose I simply import the China boundary shape file. Simply search and then further import. Okay, and now just simply find out the China boundary. So just put here the ROI and then call my table, and then I filter it, and from here I just try to filter dot equal. What's equal what? Just put here the country name, and I put the country name, suppose China. China. And further just display my study area. Suppose map.add layer, and put here that ROI, and also focus the center of this boundary shape file. Suppose map.center object, and focus on my study ROI, and then 10, and click to the run. So now it focusing your study area, which area you want to observe for LST. So this is my study area. Okay. So now for this study area, I want to observe what is the LST. Suppose in this case, I not do for the long-term analysis. So just I make the analysis for year of 2024, January to present time. What is the scenario of the LST? Okay. So for that, just we simply filtering our image collection. So for that, just take a variable. I put the variable name, suppose image, suppose 2024. Okay. Then I call the L8, because this variable stored the full image collection. Okay, for the whole world. So now we are just simply filtering. So first of all, just put the filter bounds function, then it intersecting with your study area, and my study area is the China, and it is stored in the ROI. So just I put here ROI, and further put the dot filter metadata. Suppose in this case, I want to choose only for this image, which image will be not more than 1% cloud cover. So for that, just simply write that cloud cover, and use here that less than, suppose I put here the less than 1. Okay. So now I choose only for this image, which image is the less than 1% cloud cover for my study area. And now put here the time period. suppose I put here the filter date function and put the time period, suppose year of 2024, suppose from 1st January, from present time, suppose now it's available from 2024 0918. So I simply go with this last time period, paste here. Okay. So now here I got, you can check the how much image is available for it. So just call the print and then use that the image 2024 and then use that the size function. So now it computing how much image is available for my study area between this time period. We find out that 645, okay, these 645 images are available for my study area in year of 2024, 1st January to 2024 0918. This time period we find out that total 645 images are available, okay, because it's a very large country, so that's why you can get a lot of images. So now further, suppose I want to apply the median composite using all of 645 images. Just use at the median. I take the middle pixel value and create this composite. Further, just click with my study area, which is ROI. So now we display the imagery for this time. Just use their map.add layer and call this image 2024 and click run. So now it added the layer. So we got this type of imagery here. You can see. We check the full imagery first. Okay. In this case, we got this type of problem. This problem is that we find out some place is not, there is no image. Okay. Suppose you can see in this time we find out this type of place, there is no image. It means that for this type of place, less than 1% image is not available. Okay. Less than 1% image is not available. So for that, we have to increase this cloud cover level. Okay, because this type of place is not, there is no image, this is less than 1%, so that's why you can get this type of blank. Okay, so just I put at the 10 and then try to check what happened. Okay, so now we check what happened. Still there is this type of things is not fill up. And when I increase the cloud cover level, we find out this type of white color pixel as a cloud. Okay, so no problem, I try to put here the suppose 90%. Okay, so now all of image less than 90%, all of imagery include. Okay, and when I increase this type of cloud level, then my image also added the cloud. Okay, but this type of cloud we can easily remove. Then I also show you this process how we can easily remove the cloud and get the very neat and clean satellite imagery. It loaded. or we also try to set the band combination. Suppose I put at the red, then green and blue. Stressing suppose 98%. It's working. Okay, so it's done. So now further I just click on the apply. So now this red, green, and blue visualization will be added in our map. And I also want to import, and further this visualization I want to set with my layer. So just simply copy and then paste. Okay, I put it. It's my imagery. I put the layer. So now it added the natural color band combination of your Landsat imagery. But this imagery, we find out some cloudy pixel. This type of white color indicating the cloudy pixel. Okay. So now this type of cloudy pixel, we just remove using the cloud remover function. Okay. So let's go ahead to discuss about that, how we can easily remove the cloud for this type of white color pixel. For removing the cloud, first of all, you can check your image. So you can see this is our full imagery. So in this imagery, this type of white color indicating about the cloud. Okay. So this type of cloud we need to remove. Then we also get the more better map. So now I will show you that how we can easily remove this type of cloud and then get the very neat and clean satellite imagery. So for that, simply go to the image data catalog page. So here you can see we got a one band. It's called the bitmarks for QA pixel. Okay, this is the band QA pixel. So basically, this is the pixel quality attribute generated from CFMarks algorithm. Okay, CFMarks is one kind of algorithm. So this generated from the CFMarks algorithm, and this is the band mainly we are used to removing the cloud and cloud shadow from our satellite imagery. Not only for that, other types of unnecessary pixel such as snow, or also you can see the cirrus high confidence. Also you can see the water. Okay, so different types of bit have available for this QA pixel. Okay, so now we are just use this band, and further we try to remove our cloud. Okay, this type of cloud, white color pixel cloud, we try to remove, and then we can get the neat and clean satellite imagery. Okay, so now mainly what is the algorithm for that? So first of all, we are just select the band QA pixel. Okay, and from here we set the bit number. Suppose in this case I want to remove the cloud and cloud shadow. Okay, cloud is the bit 3 and cloud shadow is the bit 4. Okay, bit 3 and bit 4 we take. Further set the bit 3 equal to 0. 0 means nothing, and also bit 4 equal to 0. Okay, so then we can get the clear satellite imagery. So for that, just I need to create a function. Simply copy this variable name QAPixel. And in this case, we remove the cloud because this place is not available. Less than 1% imagery is not available. So that's why we increase the value. Suppose I take the value 90%, less than 90%. And when I increase the value 90%, then we got this type of white color pixel. Okay. So now this type of white color pixel, we are just removing using the cloud mask function, mainly QAPixel. Then this type of cloud will be removed and we got the very neat and clean satellite imagery. So let's go. We try to remove this type of cloud. So for that, just take a variable. Suppose I put the variable as the cloud remover. Okay, you are just put in here cloud remover. Yes, please. Any question, please?
Sir, can we use here the short function here?
Yes, we can also apply the short function and we can also remove the cloud. Okay, it's also possible. Okay, actually there's a lot of way. Okay, so I will show you all time new method. Suppose QAPixel. This is the another method to removing the cloud. Okay, when you increase the level, then it also take this type of cloud pixel. Okay, it also possible. Suppose you are just take the short and apply the false boolean operator and create the marks,
Yes.
then it also possible. Okay, so this is the another
Okay.
way. So just
Thank
like take
you.
a cloud remover function, then equal sign, and then take the function keyword. I put this element name, suppose image, and then in this curly bracket I put my argument. So my argument is that first of all I just select the band of QAPixel. Okay, basically this band I want to select QAPixel. Further I set bit 3 and bit 4 equal to 0, which is indicating the clear condition of my satellite imagery, and it removed the cloud and cloud shadow from my satellite imagery. So let's go try to implement these things. Take a variable, suppose QA, and I call my element name image, and from here just select the band QAPixel. Okay, then take the another variable, suppose cloud equal, in this case just put here cloud bit number 3, and when you select the bit number, then you have to use the 1 less than 3. Okay, suppose put the 1 then less than 3. It's a one kind of syntax to select the bit number. Further I take the another variable, suppose shadow, and same process, 1 less than. This is the syntax about that, and then put the bit number is the 4 for cloud shadow, so just put here the 4. Okay, so now we just selecting our image, basically selecting our band QAPixel, as well as also take the variable cloud which stored the cloud bit number. So this is the cloud bit number, and this is the another shadow, mainly cloud shadow bit number. Okay, just be selecting the 2 bit number, cloud bit number and cloud shadow bit number. So now just set the equal to 0, cloud equal to 0 and shadow equal to 0. Then it indicating the clear condition of your satellite imagery, and it remove the cloud and also remove the cloud shadow. Try to do it for removing. Just take a variable. Suppose I put the variable name is the marks equal. So now this cloud, basically this is my band, and this band, this is the bit. Okay, here you can see this is my band QAPixel, and this band have this type of bit 0, bit 1, bit 2, bit 3. Okay, this is the bit number of this band. So now I just need to connection with bit and band. So for that, just call the QA and use here the bitwise AND function for connecting with our cloud. So simply call the cloud bit number and then set equal to 0. Okay, then set equal to 0. And also do for the same process, call the QA and put here the bitwise and further bitwise AND connecting with the bit number 4, mainly cloud shadow, and set equal to 0. Okay, which is indicating the clear condition of your satellite imagery. So further, after creating this type of things, now we need to update our image. So just put here the return this image, update marks with my new condition. Okay, this condition I want to use and update, and this condition is stored in this variable. Simply copy and paste here. Okay, so now this is the function we created. It removed the cloud and cloud shadow from this satellite imagery. Okay, and all time when you want to remove the cloud and cloud shadow from your satellite imagery, just use the same function all time. So now these things I need to connecting with my image collection. So this is my image collection. Just I put here the dot map function and call my function variable name. Function variable name is that cloud remover. Simply copy, paste here. So now let's check what happened. Just run the code. So now I hope all of cloud will be removed and we can get the very neat and clean imagery. Okay, because in this case I just apply the cloud remover function. Okay, so basically some regions such as this type of region, in this case we find out less than 1% image is not fully covered, because some region is not possible to provide the less than 1% image. I are always make the cloud formation such as river bank or coastal area. This type of area we don't find the less than 1% image. So then we need to increase the cloud level. Okay, suppose 10%, 50%, 90%, 99%. Then we find out the image, but it shows a lot of cloudy image. Okay, when I increase, then we find out lot of cloudy image. But when I apply the cloud remover function, then we can get this type of things. Okay. So now I think this we also get the some other types of white color. So I think it's the snow. Okay, it's not the cloud. So this type of things are indicating about the snow. Okay, so it's not the cloud. So it's opening. Okay, so now we also get this type of things. So some snow. Okay, so it also possible. We try to also remove this type of snow pixel and then check what happened. Suppose for that you can simply check the bit number of the snow. So here you can see snow bit number is the bit 5. Okay, so now I want to apply it. Okay, set equal to 0. So for doing these things, just take the another variable in your cloud remover function. Suppose I take the another variable for snow. Okay, then equal to 1, less than, just put here the snow bit number 5. So just put here the 5. So now same process apply again in here. Just use here the AND function and call the QA. This is bad. Then put here the bitwise and further call the snow bit number and paste here set equal to 0. So now try to check what happened. Okay. So now I hope we get the very less amount of white pixel as a snow. Okay.
Hello, sir.
Yeah, please.
Yeah, I have question like when you remove the snow or like the shadow or like the cloud cover, does it remove the ground reality? Okay, the ground truth.
So basically, it remove the not all of snow we cannot remove, but suppose it has some confidence level, suppose low, high, medium. So we just remove the suppose low, all of low snow pixel. Okay, it will be removed. Okay, but you can see also have some this type of snow pixel is also available, but not mass. Okay, so it's not affected our result. So it's the available for the snow. You can see also have some snow is also available. Okay, but now it show the low confidence, not high. When I apply the snow, then it show the low confidence level of the snow. Okay, for the ground reality, not high.
Yeah, thank you.
Okay, so now we can see now, I hope this image is also more better than previous, because first time we find out the lot of snow pixel, as well as we also get some cloud cover. Okay, so then we try to find out that more better image. Now it also look more better. You can see. Okay, so now this is my image. If you want, you can also use the other band combination. Simply click on here. And when you want to make the classification, then try to also make the one class for the snow. Okay, then you also get the more better accuracy when you want to make the land use land cover for this type of region where have the snow. Just try to remove the snow. Suppose low confidence we try to remove, because in this time if I put the high confidence, then what happened? Then this place have the snow. Then we can get the empty or totally find out the gap. We can create the image gap. Okay, because it's the snow. But when I put the high confidence, this type of pixel will be removed, and we can get only for blank or empty. There is no object. Okay, so now it also works. There is no problem. Suppose I put at the near infrared, then put at that red, and I put at the suppose blue. Okay, then we can get the another band combination. It's look more better. So this is the process. Okay, suppose this type of process all time need for the all of region, it's not necessary. Okay, suppose you filter your image collection, it depend on your study area. Okay, suppose if I work this type of work for the other study areas such as Kuwait or Bangladesh or Dhaka city boundary, then this type of things I don't need to do, because in my Dhaka city region I can easily find out the less than 1% image. Okay, in the Kuwait I can easily find out the less than 1% image. So that's why when you want to filtering your image collection and also removing the cloud, this type of things also depend on your study area. Okay, which area you want to work for this, we also defend. So in this time for my study area, China, we find out that this region there is no image less than 1% cloud cover. So that's why we are just increase our cloud cover level, as well as we also check that the lot of cloud, as well as we also find out the some sonopixel. So that's how we try to remove this type of sonopixel, and then finally we can got this type of output. Okay, but when you want to work for the other study area, we have already available less than 1% imagery, we have already available for this type of imagery, then we can easily do without this type of process, don't need. Okay, okay, so okay, so now we got this type of imagery. Okay, for that whole China boundary, basically we are just use here, you can see in this time we take the all of imagery for greater than less than 90%, all of imagery consider. Okay, and finally we remove all of cloud level. Okay, so now it's visualize. Can you see my screen properly?
Actually, you,
Voice is very slow.
right side of the portion is not visible, sir.
Right side.
Console and all that.
Okay, I also increase. Now it's, you can see.
No, it's still not visible, sir. Actually, fonts are appearing too big.
Okay, so it also show the perfect from my side. Okay, other people is also visualize. It also no problem. Okay, okay, I also see it from my another laptop. Also okay, there is no problem. So kindly you can check it for your screen. Okay, so it's also okay. There is no problem. or we can got all of code we can visualize easily. For the both of side, left and right, you can see. Okay, it's visible. Okay, all of code is visible. Yeah. So now we got this type of imagery, look like that. Okay. So now we try to develop the LST. Okay, I mean land surface temperature. And for the land surface temperature, if you want to check the workflow, suppose I simply open a paper, simply search on the Google, suppose LST. We already show a lot of paper. You also try to read this type of paper, then you can easily get the lot of idea about the LST monitoring using Landsat 8. Simply I search here. Now we can get the lot of algorithms. Suppose here you can see this is the one kind of paper. Mainly this is the main flow chart. This is the contribution of Landsat 8 data of land surface temperature in Batna city in eastern Algeria. So here you can see this is the one kind of flow chart. So basically in this case, first of all, they are calculated the thermal infrared band, then band 5, band 4, calculate the NDVI, proportion vegetation, surface emissivity, brightness, temperature, and from here they calculate the LST. Suppose I just want to follow, or you can also follow any other paper, no problem. Also you can see different types of paper, you can easily get it from the Google Scholar. So let's go try to develop a paper in method in our code. Okay, so now in this case, I want to calculate the NDVI. Okay, so previous class, I already discussed a lot of things, how we can easily calculate the NDVI or EVI or SAVI. So I hope you already know about that, how we can easily calculate the NDVI. Same process, just apply. Just take a variable, suppose NDVI, and I call my image, suppose image 2024, simply call and paste here. And then use the function normalized difference, and then I want to calculate the normalized difference between near infrared band and red band. So just put here the SR-B5, which is near infrared band, and also put here the SR-B4, which is red band. So now NDVI is done. I put here the NDVI map, just put here map.add layer and call the NDVI, and further I have to set the color. Suppose mean, I set it suppose -1, and also put here the max. I put here the suppose +1, and further just put the color plated. Suppose where there is no there is no vegetation, show as a blue color as a water body. Then put here the white color, and further put here the suppose green color. Click here. So now we can easily find out our NDVI map for the whole study area. You can easily get it for, okay. So it show this type of map here, you can see for NDVI. So this is the first step to make the LST map. When you want to using the Landsat satellite imagery, first of all, we need to make the NDVI map. So this is our first step to make the NDVI map.
Hello, sir. I have a question.
Yeah, please.
So you use like the LST land surface temperature map, but is it possible still like the under the inside the LST map we can still work like the crop or like the NDVI or something?
I don't understand your question.
No, because we use like the LST dataset, right, from Landsat.
Yes, we are using the Landsat imagery for making the LST. Yeah.
Yeah. So Landsat imagery, like it's not like the Landsat temperature, land surface temperature. LST.
Yes, yes.
So from LST also we can calculate like the NDVI.
Yes. So all of those things we can just use the Landsat imagery. Okay. And you can see this is the algorithm about that. Okay. This is the algorithm here you can see. So we first of all, this is my satellite imagery. From here we can get the data. Mainly we take the band 5 and band 4. We can get the from the Landsat imagery. And also get the band for band 10. We also get it from the Landsat imagery. Okay. And then we are just use the band 5 and band 4, calculate the NDVI. Okay. Further we calculate the vegetation proportion. Then calculate the surface emissivity. Okay. And finally we calculate the LST. This type of a step. And all of those things we will do using the Landsat satellite imagery.
Yeah, because I thought like the when we choose LST, then I thought maybe it deals with only land surface temperature.
Okay, it's not available the publicly data, so we have to use this algorithm. Okay, this type of method we follow, and then we make the LST map using Landsat imagery. But MODIS is ready-made data. Okay, basically we already know about the MODIS. MODIS we are not put any kinds of algorithm. Just we are put the band name, then we can easily calculate or estimate the LST. Okay, using the MODIS.
Thank you.
But Landsat there is no ready-made data, so for that we need to calculate this type of algorithm, and then we can easily make the LST map. Okay.
Thank you.
Okay. Okay. So now we make this type of map of NDVI we created. So here you can see this is our code for NDVI. So we can got this type of NDVI map. So if you want, you can simply just click on here and stressing. Then you also get the more better NDVI map. So it's the just I put the stressing 98%, and further when I apply, then you also get the more better map. Type of green color indicating about the vegetation area. It's a big study area, so that's why for stressing it also takes some time for creating the stressing value.
Sir, I think, sir, we should take some smaller country boundary.
Yeah, then it also more better, or a small city. Okay, then it also very quickly work. And it takes a lot of time or adding the layer or also adding the visualization. Okay. Okay, so it take the time, but approach the same. So you also try for this study area. Further face any problem, then I also guide you. But approach the same. Suppose the same things I also try to apply for another city. Just I simply change the country name. Suppose I put here that this country name, suppose Kuwait. So now all of those things will be applicable for the Kuwait city. Okay, Kuwait boundary, you can easily get it. So in this case, here you can see we got this type of map, and it's a short, not very mass big country, so that's why you can easily get the result very quickly. Okay, but for the China, it takes a lot of time. So now further, I simply click on here, and then stressing suppose put at 98%. You can see very quickly you can get the result. Just apply because it is a small country. And further we can get this type of NDVI map here. You can see, right? We got this type of NDVI map. So in this case, for my study area, you can see here, I got this type of imagery. It also show very neat and clean satellite imagery. We can get this type of satellite imagery. Okay, because I already applied the cloud remover function. Okay, I take the less than 90% cloud cover level, but I put the you can see the less than 90% image I take, but I also apply the cloud remover function. So that's why all of cloud will be removed from my all of pixel cloudy pixel will be removed during this time period. And then further we are just make the this type of NDVI. Okay, so from where you can easily get it, this type of place is the high NDVI, this is the low NDVI. Okay, if you want to check the inspector tab and click on here, then we can easily get the pixel value. Okay, about that for NDVI, you can easily get it. You can see we can find the 0.2. Okay, so now after NDVI we calculate, then you need to calculate the proportion of vegetation. So you can check what is the proportion. So basically from this paper we can also need to calculate the vegetation proportion. So vegetation proportion have a formula or equation. So when you read the paper, then you can easily get it this type of equation or this type of algorithm. We can easily visualize from this paper. Or if you want to follow the other paper, you also get this type of formula. Suppose here you can see this is the formula for proportion vegetation represent the vegetation proportion obtained according to this Carlson and the Ripley. This is the citation. You can simply check it the paper also. So this is the formula for the proportion of vegetation. NDVI minus NDVI minimum value divided by NDVI maximum value or NDVI minimum value, then power 2. So this is the formula for proportion vegetation. If you want, you can check the other paper. Suppose this is another paper. So if you want to check the formula about that LST, suppose just I simply increase the font size. Simply find out. You can see the method section. LST. Yeah, so here you can see it is the brightness temperature. Yeah, so here you can see this is the formula about that proportion of vegetation. Okay, same formula you can see. The NDVI minus NDVI minimum value divided by NDVI maximum value minus NDVI minimum value, then power 2. So this formula when I apply, then we can easily get the proportion of vegetation. Okay, so now we try to calculate this type of function. So for that I need to calculate the NDVI maximum value and NDVI minimum value I need. Okay, NDVI maximum value and NDVI minimum value I need. So let's go try to calculate the NDVI maximum value and NDVI minimum value. So just take a variable. Suppose I put the variable name is the max and I call the NDVI because I want to calculate the maximum value of NDVI from this map. Okay, and this map is stored in this variable NDVI. So just put here the NDVI and then use the function reduce region. Okay, so basically this function reduce region function calculate the statistical value, minimum, maximum. So I have to calculate the maximum and minimum. So just put all of argument one by one. Further, just make a curly bracket start and also curly bracket end. Okay, and then put here the value. So reducer. Basically, I want to calculate the maximum. So put here e dot reducer dot max. So now it computing what is the maximum NDVI for my study. You can easily get it. Geometry, mainly a shapefile variable name, which is ROI. Okay, and scale is the Landsat imagery for 30 meter. Okay, others not need, remove that. It's optional, just remove. And then further, if I print the max, click run. So now it computed the maximum NDVI value. We can easily get it from here. But it show the problem. This problem is that you can see this type of problem you also face. It show that too many pixel in this region. Okay, found this is the value, too many pixel. But max pixel allows only for this value. Okay, ensure that you are not aggregating at the high resolution than you intend. So in this time, if I increase the value, then we also get the value. Suppose I put the 100. So now try to check. Just I simply put the low resolution. Just I consider the pixel size 100 meter. It also okay. But this is another problem. This problem is that my satellite image mainly 30 meter pixel size. But in this case, I calculate this value using the 100 meter pixel size. So it's make the contradictory. So for that, we can also apply the another method. I just put the 30 and I put the another argument max pixels. I consider max pixels and I put the value 1E13. Okay, so now try to check what happened. Check. Now I hope it will work because we including the max pixel value. And max pixel highest, this is the highest value all time. When you face this type of problem, there are the lot of pixel value, then try to put the max pixel value, then I hope it will be work. Because sometimes when you want to work for the big study area, then we face this type of problem. So that's why just mention the max pixel value, then it will be work. So now you can get the result. In this case, I consider it 30 meter pixel size. Okay, and I got this type of result. Okay, we can get 0.48. So this is my maximum NDVI value. But this value have a problem. This problem is that here you can see we get the dictionary, keyword and key value. Okay, it's the keyword and key value. But for my equation, I just need only for the minimum value and maximum value. I don't need any kinds of dictionary, keyword and key value. I just need only for this number. Okay, I just need only for this number. So for that, from this dictionary, I just need to extract the value. Okay, so from this dictionary, just extract the value. So for that, just use here the dot values function. So now it extract only for the values, and this value I get from first item. So basically it's the only for the one item. So it's the first item. Okay, and first item consider as a 0. Okay, 0 indicating the first item because it start counting from the 0. 0 means the first item. So now if I run the code, now I can got only for the value. It show the computed object. Just we got only for the value, maximum NDVI value. We got it. Okay, without dictionary. So I can see it only for the value. Okay, but this value show the computed object. But this value I need to use as a number. Okay, so I need to use it as a number. So for that, just add the e dot number function. So now it computed as a number. So if I run the code, you can see it show the number computing. So further, this number I can easily use for other equation. Okay, so now it's ready to use because first of all I got the dictionary. So for this dictionary I can just extract the value. Okay, and this value show as a computed object, but I need the number. So for that, just use the e dot number function. So now I now I use it as a number in my equation. Same as for minimum NDVI, just simply copy the same code.
Sir, how does it matter? But basically, the value remains the same.
Okay, so basically a scale value, it shows the same value, but it also more better to use the proper scale. Okay, because this scale is the Landsat is the 30 meter, so that's why we try to use here the 30 meter. Okay?
Otherwise, technically, it has no significance, no, sir?
Yes. But it's not much more different. Okay, it's not much big. Suppose 0.1 or 0.2 difference when you want to increase the value other things, but almost it's the same. We got.
Right.
So now just paste here. I change it the variable name, suppose mean, and I put here that mean. Okay, and then further print the mean if you run. So now it computed the minimum NDVI value. We can get it from here. Okay, so you also need to print the max also. Okay. So now we can.
Sorry,
Yeah.
sorry. Is it possible here if I use in our dictionary under this reducer head min and max, then can we simultaneously both the values can be displayed?
Yes, it also possible. Suppose at the same time we try to add the mean and max value, but in this case my formula, you can see what happened. My formula is that minimum NDVI for single. Okay, also maximum NDVI single. Okay, then minimum NDVI. So that's why 2 times we are just calculated minimum and maximum. So further I can simply input in my equation mean and max. Okay? But if you want, you can simply put the mean max value, then at the same time 2 value appear. Okay, but it is stored only for the single variable. Okay.
Okay, sir.
So now we try to calculate the fractional vegetation or proportion vegetation. Just take a variable, suppose fb, or you can put any variable name. So now we try to calculate the fractional vegetation. And this vegetation, fractional vegetation, you can see this is the formula. We are just apply this formula: NDVI minus NDVI mean value divided by NDVI max value minus NDVI mean value and power 2. You already know about the different types of method. Previous class I discussed to calculating this type of equation. We can use the expression, we can use the direct equation. Okay, different way. So now let's try to calculate this type of equation. So for that, I want to use, suppose, I just call I put the rate equation, suppose NDVI. This is my NDVI map. I simply call the NDVI because here you can see this variable stored the NDVI map. So just I put here the NDVI. This NDVI subtract with minimum NDVI value. So put here the MIN, mean. Basically this variable MIN, mean. And further it's divided with maximum NDVI value subtract with minimum NDVI value. So just I call the max. These things subtract with min. Okay. So now we have also need to use the power 2. Okay, for the full equation. For the full equation, consider just make the bracket start and also bracket end. Okay. So now I put the power 2. So for that, put here the dot POW. It means the power. And 2 is a number. So for that, use here EE dot number and put the number 2. Okay. So now it create the fractional vegetation. So we have just put this type of equation. You can see. You just put here that NDVI minus minimum value. We already calculate the minimum value. Then divided by maximum value. Subtract with minimum value. We already calculate. Okay. And further power 2. 2 is a number. So we have to put the E dot number. Okay. So this is the equation. You can simply put in here and calculate the fractional vegetation. And then I just rename it. Suppose I put the rename these things. I put the rename as a suppose FV or fractional vegetation. You can put any name. So now just add the layer. So map dot add layer and call the FV. Click to the run. So now it's generating the fractional vegetation layer. We can easily get it from here.
Yeah. Hello, sir. I have question one here. So you said you rename the layer, right? You rename the layer, the new layer. Yeah.
Yeah. So basically,
So,
okay. So when
but
I
like the
rename it, yeah.
yeah.
Okay. So when I rename it, then we can get the layer name. Suppose when I just click on here, we can get the layer name is the FV. Okay.
But you cannot use this FB in your map layer, right? Like the when you like to print the map.
Okay. So this variable can be anything. Okay. Suppose you can see, I put here the small FB. There is no problem. It's a variable. Variable can be anything. Okay. So this full thing is stored in this variable. Okay. And I put the layer name is the FB. Okay. So that's why this FB you can also get it in here. Okay.
So if you put like the different name, I mean like the, let's say Kuwait,
Okay,
and
any
then
name you can put, any name, no problem. Name is nothing. So variable name can be anything. You can put the any band name in here. You can put the any name also. If you want, you can also put here the any name. Also, there is no problem because variable can be anything. So now you can
but like the
yeah.
map add layer should be like a different name, right? Is that?
Yeah.
For example, yeah.
Okay, so if you want, you can also put any name. Variable name can be anything. Suppose now this full equation is stored in this variable. Okay, and I put this layer name as the FV. So that's why we got it as the FV in here. Okay, in my band name. Okay. So mainly this fractional vegetation show as the band. Okay, it's a band. Further, you can see when I calculate the NDVI, I don't put any name. So then you can see what happened. I don't put any name. It shows the default name ND. ND is the default name. But if I use the dot rename NDVI, then it shows the NDVI, not ND. ND is the default. Okay, if I not use any rename, then it show the ND. Okay, but in this case, if I use the FV, so that's why when I open the layer and then just show, suppose it show the FV. This is the band name. So further, when I need this type of band, I simply use the FV and then use it, because further I also need to use it for calculating the emissivity. Okay, for the when I calculate the emissivity, then I just call the FV band name. This is my band name. Then we can easily work with that.
Thank you. Clear.
Further, we try to add the color also. Suppose I put here the color from here. Suppose blue color. Then put here that white color, or put here the suppose this type of green color. So for vegetation, apply. So now it create the fractional vegetation layer. Okay, we got this type of map, and we find out only for this type of place have the vegetation. Okay, type of. Just I import, and further this color I want to input in my layer. So for that, copy this variable name. You can see this is the variable name. Copy and paste after the layer name. So this is my layer name. I put here, okay, and then I put the layer name. So in this time, you can see it show the layer name is the layer 4, but I want to display the layer name. Suppose I put the layer name is that fraction vegetation or proportion vegetation. I put the fraction vegetation. So now click to the run. So now it also added the layer name also fractional vegetation. You can see. So this is our another step. We calculate the fractional vegetation. Okay, using this formula. Okay. Further, we need to calculate the emissivity. Okay, you can see the emissivity. Emissivity can be calculated by using this equation. Mainly, you can click on here, then you can easily get the cited paper. Okay, about this equation. So this is the equation. You can see emissivity. Okay. So in this emissivity equal to 0.04 fractional vegetation plus 0.986. So now I want to apply this formula and then calculate the emissivity. Okay. So now let's check. We try to apply these things in our formula. So now let's go. We try to write the code. Okay, so now further, just take a variable. Suppose I put the variable name is okay. So first of all, these two value here you can see you got the two value 0.04 and 0.986. These two value I just simply store it in a new variable. Okay, suppose A and B. Further, I want to make the equation. Okay, so further, just take a variable suppose A equal. I put the E dot number because it's a number. So put here E dot number. I stored the number suppose in here 0.004. Okay, and take the another variable suppose B, and then I simply put here E dot number. So just I simply stored this to constant value in a variable. So further I simply use this variable and I can make the equation easily. So just put here 0.986. Okay. So just I stored the A and B. These two variable I stored. So now I just simply write my equation. So just I take a variable. Suppose EM surface emissivity, or you can put any name. I put the EM and I call the fractional vegetation, mainly FV. Okay. This fractional vegetation multiply with 0.986. Sorry, it multiply with, I check the value. It multiply with 0.004. You can see it multiply in here. So we try to apply the same process also in here. It multiply with A. I simply call the A because 0.04 is stored in the A. Just call the A. Okay, and then add with 0.986. So just put here the add and apply the 0.986. Okay, and if you want, you can also put the layer name. Suppose just put the layer name. I put the dot rename function, rename, and put here. Suppose I put the layer rename. Suppose EMMM, or you can put any name as a thing. Just add the layer. Suppose map dot.
So should we write B in place of 0.986?
Yes, we have to write it because we can get it from this paper. So here you can see And you can see emissivity can be calculated by using this equation. And if you want to check the citation, then you can easily get the citation where we can get the equation. Okay. So just use it as a reference. Okay. So basically, it's a constant value, and it's developed by other scientists.
No, that's right, sir. But simply in our expression, actually, we have already already mapped through variable b, no, sir?
Yes, yes. Variable b is already stored at the 0.986.
That's why I am saying in place of 0.986 in your expression.
Yes, yes, yes. You okay? Now got it. Yeah. We have to put the b because b is stored at the 0.986. Thank you. Okay. So now it's okay. So now because we already stored the a and b, these two values. So further we simply call the and add with b. Okay. So now it's okay. 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 So now we add the layer em.
तो जिंदगी में खाना कुछ कर मिला कुछ भाग में साथ हो गया अगर बात बहुत तेज पकड़ी है भाई मम्मी को कहती थी भाई ये वाली मम्मी कहती थी गुड्डू के सोते हैं देखती थी ना एक्चुअली
So now we got this type of emissivity layer. So it look this type of layer here. You can see forward study area. So just I try to add the color for the more better visualization about the emissivity layer. Just stress about 98%. Or if you want, you can also add the color. Suppose I put the here is the low value, show this type of blue color. Then greater than show this type of green color. Greater than show this type of suppose yellow color. Yellow color. And high value show as a red color. It's the high emissivity indicating apply. And also import. So now we got this type of map. It show this type of map. Okay. So if you want to change the other, suppose it show it's not look more beautiful. I want to change it. Suppose I want to apply it for 90% and then check what happened. Okay. We got this type of visualization. Suppose I put here that stressing 3 sigma. Okay. So now it's I think it look more better. Or 2 sigma. Just check which one is the more better visualization. Then try to use it. Okay, suppose I want to use it. And further try to import again. Import again. And copy this variable name. And add this variable name after just em. Just put here. And I put the layer name, it's a m. So run the code. Okay. So now we got this type of surface emissivity map we created. And now we talk about the brightness temperature. Okay, basically band 10. Okay. So basically from the band 10, we can generate the brightness temperature or thermal infrared band. So this is the band. It's called that band 10. Yeah. You can see this is the STB10. Okay. We can easily calculate from the brightness temperature from here. And this unit is the Kelvin. Okay. This unit is the Kelvin. But further we can easily convert into degree Celsius easily. This unit is the Kelvin. Okay. So now we try to calculate the thermal band 10 and then we calculate the brightness temperature. So basically now this is the ready-made band. So that's why we are not taking any kinds of calculation. Just we select the band and work with that. So let's go. For that, just take a variable Suppose I put the variable name is that suppose thermal, and now call the image. So basically in this case, this is my satellite imagery, image 2024. Okay, and from this imagery I select the band, to put here the select, and put here the band name is the STB10, STB10. Okay, so this is the band name, and this band is very important to calculating the surface temperature. And this band have already, we can got this type of scale value and also offset value. Okay, so this band is needed to rescaling when you want to get the more better pixel value of LST, because our maximum result depend on the thermal infrared or band surface temperature band, and this is the band 10. It's the surface temperature band, or also called the brightness temperature band. So now we need to compute it, the proper pixel of brightness temperature. So that's why this type of scale and this type of offset value we also need to use. So for that, simply copy the scale value. This is the scale value. I just put in here and multiply with here, multiply, okay, and then add with offset value. Basically, this is the offset value. Okay? Then we get the proper pixel of brightness temperature. Just add it. Okay. So now we try to add this thermal band as a layer, or if just simply add the layer. Suppose just I map dot add layer and call the thermal. So now we added another layer of the thermal band. It look like that. Just click on here. So this is 98%, and further apply. But if you want, you can also put here the, suppose just put here the plated, and I want to add the color. Suppose blue for blue, then green, and yellow. Red. I put suppose stressing, this stressing, and then apply. Okay. So now in this case, it creates another problem. This problem is that in thermal band, we find out this type of line. You can see, we can got this type of line or scale line error. We find out in here this type of imagery. Okay, so it creates another problem. Okay. So we need to remove it to get the proper LST map. Okay, all time it's not happened, but some region or some time for the atmospheric correction, or sometimes we need this type of correction. Suppose in this time we got this type of scale line error or this type of error. So now, okay, so we try to make the map first, then we try to remove this type of line. Okay, otherwise it not look more better. So just I try to import, and then further copy, and then paste here, and I put it say thermal or brightness temperature, just click on. So now we get this type of things. In the final stage, now we come in this final stage, basically we calculate this type of equation. So here you can see this is the equation for land surface temperature. So ST mainly land surface temperature, TB mainly is the satellite brightness temperature. Okay, so satellite brightness temperature Kelvin unit. Okay, we already calculate the TB, mainly thermal band. We already calculated. then divided by 1. 1 is the constant value plus lambda. Lambda is the wavelength of emitted radiance. So this value is the 11.5 micrometer. And rho is also constant value 1.438 10 inverse 2. This is the rho value. And further multiply with logarithm emissivity. Okay, E means emissivity. Okay, so this emissivity we already calculated using this formula. So now we try to develop this type of things. So in this case, TB is the ready. We already calculated the TB, as well as we already calculated the emissivity. Okay, and the rho and this lambda and 1 and 273.15, it's the constant value. Okay, rho, lambda, 1 and this type of value is the constant value. So further, in this case, we are already calculate the brightness temperature band and also calculate the emissivity band. Yeah, so now further, it's a constant value. We can easily get it from here, as well as 273.15. Basically, it's subtract. When I subtract this value, then we can easily get the result degree Celsius. Okay, so when I subtract, then we can get the result in degree Celsius. So now we try to calculate this type of equation in our code and then check the result. So let's go. So for calculating this type of equation, we can apply the different types of way. So one way is that simply take a variable, suppose LST, then equal. So in this time, if you want, you can also apply the expression. So just I call the thermal, okay, or brightness temperature, and I apply the expression on this thermal. Okay, so now just put the equation one by one. You simply put the equation. So just take the bracket and I put here the suppose TB, brightness temperature, it divided by 1 plus, now we put here the value only 0.00115. This value, it's multiply with TB, mainly brightness temperature, divided with our 1.432, just put at 1.438, and then finally this equation multiply with logarithm. So just put at the multiply log logarithm, we take your emissivity. I put it suppose EP. So in this case, this is the equation. So TB mainly brightness temperature, and 1 is the constant value, this type of constant value lambda or rho. Okay, we multiply at the same time and then write the value. This multiply with the 1.438, mainly this is the another value, and logarithm mainly EP. EP means that emissivity. So this is my equation. In this equation, we can just only for the two variable. One is the TB, another is the EP. So now further just put here the comma sign and take the curly bracket. In this curly bracket, just you define what is the TB, what is the EP. Okay, then it will be done. So let's go try to do it. So basically I put here the TB. TB mainly come from this thermal, basically this variable thermal. Okay, if you want, you can simply put here the suppose select the band name STP10. Okay, further comma sign, and EP means emissivity, so call the EP, and it also come from this basically EM. So you can say I already make the layer name EM. Okay, EM. I put the band name is the EMM. So I simply call the EM, and then select the band name which I put EMM. Okay, basically this band name which I put in here EMM. Yeah, this one, this name. Okay, and this is my layer name EM. Okay, from this layer I select the band of EMMM. or you can put any name. If you want to use the same name, also there is no problem. Okay, and further I put the rename. Suppose I put the rename as a suppose LST. But when I apply this formula, then I got the result in Kelvin. But I need the result in the degree Celsius. For the degree Celsius, simply put the subtract 273.15. Then it convert into degree Celsius. So now we try to add the map. Suppose map dot add layer and call the LST. Click the run. So now it added the LST map for our study area. We got this type of map, white color. So we add the color first, then check the visualization. Okay, so just click on here. You can say the LST because I already renamed it, so that's why it's for the LST. Best thing we can do. Okay, I put here the color range. Suppose this type of color for the low, only 26 below or 26. Or then put at that green, greater than put at the yellow, or high temperature show as a red color. Okay, so now you got this type of map, but this map has some problem. This problem is that it show this type of line. Okay, so now how we can fix this type of map line? Okay. Map is okay, there is no problem, but we can get this type of visualization. Okay. So if you want to check the value, suppose click on here, then we can get for this type of value. What is the LST for this coordinate? We can check it. We can get the value. We can see 55 degrees Celsius. We got it. So now I hope this problem is occurred because in this case, we try to add the less than 90%. So it including all of images, which is not needed for this place because this place is already available less than 1%. But I put the all of less than 90% immediately. So this is the one region. I don't know what happened. Is this the one region? So it combined lot of images, but all of images is not necessary for my study area. But I put all of images. So this is the one region. So in this case, I try to fix it. Suppose I put the less than 1%, and I am not applying the cloud remover function. It's not need for my study area, for this study area, because this study area is already available. Less than 1% image is available. So now try to check what happened. Okay, it is still so, but not mass. I just try to run the okay, just stressing. Okay, just click on here, and I want to stressing. Suppose 98%, and add the plated. Suppose low show as a blue color, then greater than green color, then put at the yellow color, and put at the red color for high temperature. Then and also import. Okay, Now we got this type of visualization, not more. Okay, so it now also visualize more better. Yeah. Okay, so basically it's a desert or sandy land. So that's why the reflectance, this type of thing. So that's why you can get this type of visualization. Okay. So if I stressing the other, so I put the stressing 90% or stressing free, then check what happened. Suppose put the 90% and apply. So now let it look like that. Suppose stressing 3 sigma. We got this type of visualization. Or put at the 90. 90 is okay. Try to put the 90. It was more better. Then we can easily visualize the red color. It indicating about that more than 58 degrees Celsius. Okay. This type of color, red color, indicating about the more than 58 degrees Celsius. Okay. And the blue color is the 34 or below to the 34. Okay. This type of blue color. Green and yellow is the medium. Okay, or moderate. We can get this type of things. So here you can see you can got this type of map. Okay, and further if you want to check it, the value, suppose I want to check this type of red color, just click on this red and click on this red color, then we can easily get this result for the LST value 60. Okay, greater than 58. Okay, so this type of red color including about the more than 58 degrees Celsius. When I stressing, it also show the value. Okay, 58 or more than 58 we can get all time. So if I check this type of green color, click on here, we find out the 49 degrees Celsius. Also you can see this type of blue color. It's also lower temperature, we can get 35 degrees Celsius indicating. Okay. So this is the one process to make the LST map in Google Earth Engine. If you want, you can also use the same code. I think it's the sharing. Can you see my screen or any problem, anyone? Is it visible properly or not?
Yes, I think visible.
Okay, okay. I think it's also okay. Yeah. Okay, so we can got this type of map. And suppose now I want to check about the urban heat island. Okay, so basically when you want to define the urban heat island, then it's more better. You can simply choose your urban area or study area as the urban. Then we can easily get it the nearby area in the urban. We can get the high temperature in the urban. Okay, then nearby. So now suppose I simply change my study area. I want to put any urban area, and further I want to calculate the urban heat island. So then we can easily find out that high temperature in the urban heat island. Okay, for their periphery region. So I want to add suppose in Dhaka city, or okay, just a minute. I want to add for why is that? Okay, so I will show the example for the Dhaka city boundary. You also try to for your own city area, then you also get the more better visualization. Okay. Suppose just I import and further I just commenting my previous line and I put the name as a ROI. Okay, ROI. So now if I run the code, then we can get the result for Dhaka city boundary. Now I run the code again. What is the problem? Sorry. I put the name as a ROI. Okay. So now I can easily detect about the Dhaka city urbanite island. So first of all, we create the Dhaka city map. Okay, just we create. We got this type of result. We need to change the visualization parameter. Okay. Suppose just click on here. And then we simply stressing 98%. Just apply. We had also add the color. Suppose I put here the color blue color for the low temperature. Get then use here the green color. Then use here the yellow color. And put here the red color. Apply. And further just import this color. So we got this type of map here you can see. Okay. So basically this type of red color indicating about the high temperature. This type of blue color indicating about that low temperature. So basically it is the water body. Water body can get the low temperature. Okay. If you want to check the value, suppose just click on this type of value. Suppose click on here. We can easily get the more. You can see what is the value. 39 degrees Celsius. This type of indicating about that. Yeah. 41 degrees Celsius. And if I click on the any blue color, it is the lower temperature. Okay. For the water body, it absorbs the temperature. So that's why you can get that low temperature value for this type of water body. Just click on here. We get it 26 degrees Celsius. This type of water body. Okay. So now we try to create this type of map for LST. Okay. So now further, I want to check the temporal analysis, basically temporal change of LST value for this time period. Okay. So now we talk about that how we can easily create the time series chart of this LST. Suppose in year of 2024, January to present time, what the changes, where the high temperature, where the low temperature. Okay. Or also we calculate the minimum, maximum temperature for this time period, then we can easily do it. So now anyone any question about the full code, you can ask me. Basically this time we talk about the lot of topic. Step by step I try to explain. It look like that because we need to change the stressing level. Okay, just simply change the stressing level, then it also works. Okay, because I try to use for it another study area, so that's why it look like that. So now you can see we can get the LST, then we can calculate the thermal, then emissivity, then fractional vegetation, then NDVI, and this is our satellite imagery. Okay, we can calculate this type of satellite imagery. It also look more better when I just simply stressing. Suppose stressing 98%, then this imagery is also look more better. Suppose you can see now we can got this type of imagery. Okay, so this is our imagery. So we can simply take the Landsat imagery, and further from this imagery you can calculate the NDVI. Okay, so this is our NDVI map. If you want, you can also stressing, then we also get the more better NDVI map for visualization. Just apply. So now you can got the NDVI map. So this is the vegetation. Okay, you can easily get this type of green color indicating about the vegetation. And further we calculate the fractional vegetation. This type of fractional vegetation we can calculate. Then we calculate the surface emissivity. Again, this type of red color indicating about the high surface emissivity. And further we calculate the thermal. So we can get this type of thermal. And from the thermal we calculate the LST in the degree Celsius. Okay. So now any question about that, you can ask me for any confusion or any step.
Hello, sir.
Yeah, please.
Maybe, yeah, I have question about the, you showed like a 98%, then after that you showed like a 3 sigma or something. Uh,
Okay, so
yeah,
basically
what's the
for
difference
the
between them?
stressing, we are using at the different types of level. Stressing 1, stressing 2, stressing 3, stressing 90, 80, and 100. So basically here you can see when I put the stressing 1, you can see what the range we can got. We can get the 31 and 36. Okay. When I put at the stressing 2, then you can see what happened. We can get the 29 and 38. Okay. When I put the stressing 3 sigma, then we can get the 27 and 40. Okay. So it's the different types of range. Okay, for when I put the stressing level 1, then it provide the visualization using this stressing level. Suppose in this time when I apply the stressing 3 sigma, it show the 27 and 40. Okay, so all of 40 greater than 40 or 40, all of visualization show as a red color. Suppose in now I apply the code, so now we get this type of red color. Okay, this type of red color indicating the temperature 40 or greater than 40. Okay, and blue color indicating the 27 or below to the 27. Okay, and green and yellow is the moderate between this time. When I put here, suppose stressing level 98%, then we can get the 41. Okay, so this type of red color, if I apply, so now this type of red color indicating the 41 degree Celsius or greater than 41 degree Celsius, this type of red color on my map. Okay, and this type of blue color indicating the 26 greater than 26 or lower than 26 degree Celsius, and yellow and green, it's the moderate. Okay, so for
Sir,
the yeah, please.
sir, I do have one query, sir.
Yeah, please.
Simply by changing this stress level, the lower and the upper limits are changing.
Okay, so basically it not changes, it just show the visualization. So we are just set the upper limit and lower limit and then choose the visualization, but not changing the actual mean and max will it not change.
Okay, okay. That means actually when I will actually see the temperature, suppose in LST
Yes.
map, then that will show the actual temperature, na sir?
Yes. Not only for that, if you want, you can also put the custom. Supposing the custom.
Right, sir,
Suppose
right,
I
sir.
want to put the custom value. I want to show the value, suppose 30, and I put here the suppose suppose I put here that 44. Okay, so now it create this visualization based on my range. Okay, so based on my range, I got this type of visualization. This type of red color pixel indicating the 44, and this type of blue color in is the 30 or lower than 30 degree Celsius, indicating this type of blue color, or any specific
Right,
range we can put in here. So it also provides this type of stressing level. You can see 98%. Then it automatically set it upper limit and lower limit. It's not the actual mean and max value. Just
Okay, sir.
yeah. Okay, I hope you got the idea. Yeah. Okay. So now we got this type of map for our LST. So now we talk about the time series chart, how we can easily create the temporal analysis. So when it will be high, when it will be low temperature, or one day, what is the maximum temperature, what is the minimum temperature, or average temperature, how we can easily make the time series chart. About that, we discuss about that. So let's go ahead and discuss, and further we discuss about the urban heat island. Okay. So for the time series chart, when you discuss, so we are applying the same process, okay, because it's a totally unready-made data set. We already know about the unready-made data set. For the unready-made data set, mainly we need to create the band. Okay. So in this case, I want to make the time series chart for LST. So for that, I need to create the band of LST. Okay, I need to create the band of LST, and further we can easily visualize our result using the unready-made data set. Okay, we already know about that, how we can easily create the band. So for that, just take a variable. Suppose add, I put the add LST equal and function keyword, and put the image img, and curly bracket, just put our argument. In this time, my argument is that I want to calculate the LST, and further this LST I want to use as a band. Okay, and this band further I just simply connecting with my image collection, and then we can easily make the time series chart.